So, hello everybody. I'm the organizer of the last mini symposium in this fantastic conference, MoCCA'. Um, this the last one is about algebraic techniques in combinatorics, and our first speaker is Cosmin and from Yale University. And he's going to tell us about Trifference Problem and its connection to some TCS problems. So Cosmin, take it away.
Thank you very much, Zilin, for the invitation, and thank you to all the organizers for having me. Before I begin, I should say that this is joint work with my amazing young co-author, Dmitry Zakharov from MIPT, who I think you might all know in this room. Since this talk is happening during the Spain-Switzerland Euro football game, I promised that I'll go a bit gentle and give you an opportunity to pay attention to the TV if it's in the background, or to turn it on if you haven't done that already. So my goal rather than to tell you all the things about my result with Dimitri would be to really give you a gentle introduction to this problem, which is actually one of my favorite problems nowadays, and to tell you a bit about what got me into it and some of its connections to some other problems in extremal combinatorics that, have seen a lot of exciting developments using algebraic tools. So I thought this would be maybe thematic for this section. So let's start with the definition. A set A in this box with k letters, let's call them from 0 up to k minus 1. So n-dimensional vectors with coordinates in the set. We're going to look at sets that have this property that for every k distinct vectors in A, there is some coordinate where all of them get pairwise distinct values. And such things are called perfect K hash codes. And so they're actually some important objects in theoretical computer science. I won't really say anything about the theoretical computer science part, but as one can imagine, it's not too difficult to imagine that such things are useful, as one in real life usually has, one encounters the problem of encoding some data set into a set of vectors, and one would like to do that with some kind of distinguishability property for the vectors and do it efficiently. So constructing codes with such features is rather useful. We will look at the problem of how large can they be, which is a more, let's say, combinatorial problem, more traditional combinatorial problem. So to get that thing started while we're parsing the definition, let's take the baby case, the first case where this problem makes sense, k equals 2, in which case the question is, what's the maximum size of a subset of the hypercube such that every two vectors must have, well, a coordinate where they're distinct from each other. So it takes a second to see that this is not really a meaningful question. All I'm asking from this set is to have, well, for every two vectors to be distinct in it. So what, you might as well take the full hypercube. So the answer is not very interesting in this case. But however, once you enlarge the alphabet just with one letter, the problem becomes quite interesting. So if I give you a set A and with n-dimensional vectors with coordinates 0, 1, or 2, with the property that for every three distinct vectors x, y, and z, there is some coordinate I for which, well, the set of coordinates xi, yi, and zi is just the set 0, 1, and 2 in some order. Well, understanding the maximum sizes of this is really a wide open problem. And perfect 3 hash codes are also called Trifference sets. And the problem is really called the Trifference problem. And perhaps a good visual if you're a betting man. When you see one of these machines, this Trifference problem is really asking, well, for the opposite really of what you would like to see when you're betting on a slot machine like this. So you would like really the vectors to be all distinct in that coordinate, not all equal. Okay, so let me give you an example. It's a classical example of Conway and Sloan for this problem. It's not that easy to actually find examples if you try to do this by hand. But here's one, a non-trivial one in 4 dimensions. So this is a family of size 9 that has this Trifference property. Namely, if you pick your favorite 3 vectors in this list, I don't know, this one, oh, let me not underline there. The second one, let's say, anything you wish, then you can really spot easily some coordinate, right, where the values are distinct. Let's say the first one in this case. So this is a concrete example. It's kind of an interesting one. Perhaps a less obvious property that it has is that this is actually a 2-dimensional subspace of F3 to the 4. In fact, Conway and Sloan were interested in linear Trifference codes. So these are codes that, well, when you regard the set 0, 1, 2 as the finite field with 3 elements, and you incorporate this vector space structure, well, it's also a worthy object to study linear Trifference codes, so Trifference sets that are subspaces. And so yeah, it's an interesting question how large they are as well. In general, how can one find examples of Trifference sets? One can prove pretty easily that there are exponentially large Trifference sets by doing a standard deletion argument. Take a random set of vectors and you delete one from each bad triple. That leads you to some exponential lower bound. One can do a bit better, and this is what Corner and Martin did in general. So the size of the largest Trifference set in this box, which I'll denote by T3 of n, turns out is at least this quantity 1.158 to the n, and this well, it actually also uses some probabilistic deletion. However, it's less naive and makes use of this example of Conway and Sloan in some base case. So it's some kind of marriage between a probabilistic construction and a product construction. That's a bit more typical. Okay, so this is the state of the art for lower bounds. Before I tell you about upper bounds, let me revisit these questions that I want to connect this problem with. So the first one is the cap set problem, which asks for, well, the maximum size of a set A in F3 to the n, which does not contain any non-trivial solution to this equation, x plus y plus z equals 0. I'm assuming that most people in this room have seen this, so I'll jump quickly. Equivalently for us, this is, well, perhaps best reformulated in terms of asking for a set A in F3 to the n to have this feature that there is some coordinate I for which the sum of these values, xi plus y and zi, this is non-zero, which can be picked up by a degree 2 polynomial that vanishes when you plug in xi, yi, and zi. And this was a valuable observation in recent work on this problem. And I would be remiss to mention this without telling about these 2 results. So this is a famous problem by itself, but it's also the finite field analog of this problem of finding the largest subset of the interval from 1 up to n without non-trivial 3-term APs. And both of these problems have seen recent exciting progress. The original cap set problem using this very easy algebraic observation saw an amazing breakthrough thanks to the work of Krudlev, Pak, and then Ellenberg and Geisweit, who showed that, well, the size of this largest cap set is at most a constant to the power n, where this constant is strictly less than 3, in particular this 2.56. And then Bloom and Sisas for the integer problem show that, well, this largest 3p free set has size at most n divided by log of n to the 1 plus epsilon, which was a long-standing conjecture. Okay. Let me mention a second famous problem in combinatorics, which again, maybe all of you might have heard of, the sunflower problem. And maybe I'm abusing really the expression sunflower problem here, because I think multiple problems go under this thing. But for us here, I mean just the sunflower problem with 3 petals where you fix the ground set to be 1 up to n. So this is asking for the maximum size of a collection of subsets of 1 up to n. If there's no non-trivial triple of subsets satisfying this equation, in other words, no 3 distinct sets A, B, and C that look like this, the intersection of every 2 is the same. So this is this is band. And equivalently, in terms of vectors, this asks for the size of the largest subset of the cube, with the property that for every 3 distinct vectors, x, y, and z, there is some special coordinate where there's again a very low degree polynomial that picks up this information. There is some coordinate I where the sum of the values xi, yi, and zi equals to 2, which is easy to see. So if a set A doesn't have 3-petal sunflowers and no structure like above, well, then it means really that you can right, there must be some coordinate where the corresponding index from 1 up to n must actually lie in just precisely 2 of them. Right, the 3-petal sunflower has this feature that every element lies either in 1 of them or in all 3. So a bit of reformulating leads you to this, and this was again very useful, and it provoked some exciting developments based on the work of Krudlev and Pak, and more specifically Naslund and Sawin, building upon reformulation of the Ellenberg-Geisweit argument using the slice rank terminology. So can be adapted, and you can derive this bound. And maybe I should help maybe write some tensors here. So for the 3 AP case, the capset problem, the idea of tau was to define this map from f3 to the n times f3 to the n times f3 to the n, which is diagonal on when you restrict it to the Cartesian product of A with itself. And so one can hit it with a slice rank. So the slice rank of this tensor on this restricted to A times A is just A, and one can upper bound the slice rank in some non-trivial way. For 3-petal sunflowers, let me use this. The tensor, you could guess, based on the above, well, it's this tensor, the product of all coordinates of this polynomial above, which again, you would like to say that it's diagonal on the Cartesian product, and you could hit it with slice rank, except, well, a slight problem. It's not really diagonal. You could have, for instance, one of the sets contained in another, and that being the core of like a rather silly sunflower thing here. So this is not really diagonal if you evaluate the tensor at this triple of vectors in A that are not all distinct and look like this. Well, you're going to get some non-zero value there. But, well, one can just pass to subsets of A that have, well, the same cardinality. So that was the trick here. And do the summation over all the, well, so L inside. And still apply slice rank. The slice rank on this smaller, well, stronger restriction works. Okay, so this is the story of capset problem and the sunflower problem. Let's get back to the Trifference problem. So the Trifference problem, I remind you, asks for the maximum size of A in the box, so that for every 3 vectors, there's a special coordinate where they're all distinct. And at first glance, yeah, it looks like a problem where there's much less structure than in the previous 2, right? The one was about 3-term progressions, and the other one was about sets having some funny thing. And remember that this problem is not really specific to the alphabet 0, 1, 2. They're just like the first three symbols that come to mind, I guess, in the mind of a computer scientist instead of 1, 2, and 3. Okay, it might look a bit different, but it turns out, well, this one can twist this artificial. One can formulate an artificial structure by replacing this alphabet conveniently. So if you replace 0, 1, and 2 with these cube roots of unity, 1 zeta and zeta squared, where this is a primitive cube root of unity, well, this condition that these guys are distinct is completely equivalent with the fact that the sum is 0. And so one can hope to hit it with slice rank, like for sunflowers, it's almost the same polynomial up to this constant of 2. And turns out this is indeed possible. All you have to do is write down this tensor, product over all coordinates, this guy, and try to hit it with slice rank again, except again, you're going to face a problem. It's not really diagonal, but it's again, and a couple of ways. Perhaps the most elegant would be to, well, apply not slice rank, but so-called flattening rank, a new notion of rank introduced by Correa, Sudakov, and Tomon actually earlier this year, I believe. So something like this is correct. And I won't really get into details of what this means. It's a twist of the usual slice rank definition, and the upper bound for this tensor, for the flattening rank of this tensor is the same as the upper bound for well, the slice rank of this tensor for the sunflower problem. So it's not a coincidence that you get exactly the same constant there under the exponential. Okay, so oh, I forgot to mention here. I apologize. So this flattening rank Correa, Sudakov, and Tomon, I believe. Okay, good. So we have a bound, a non-trivial bound for the Trifference problem. A is at most 1.889 to the n. So here comes the first element of surprise in this story that really got me excited. So turns out one can take further advantage of this artificial structure that you can create by replacing the alphabet with cube roots of unity to prove an even better algebraic argument. And so it turns out you can prove that a Trifference set has size at most 1.732 to the n, which is a bit interesting if you have worked on problems with slice rank and capsid problem and things like this. Beating the slice rank for a problem where it gives already non-trivial information, it's kind of interesting. So turns out the proof is very simple. So we're actually, where does this constant come from? We're actually show that this is true. The size of H is 2 and most 3 to the n, and it's a proof by using the linear independence trick in the style of how it's used classically for the two distance problem in R to the D or the few distance. If I give you a set of points in R to the D with two distance, how large can it be? What was the idea? For every pair of distinct elements in A, you consider the 2n varied polynomial, which is this. You can check from how it's defined that it satisfies a bunch of good things. So first, okay, the coefficients are complex numbers. This is just to remind you that I switched this alphabet, and now these elements of A are these cube roots of unity. Okay, perhaps more importantly, if you plug in some pair X, Y that's different than the pair AB, well, among these four guys, there must be three that are distinct. And so there must be some coordinate, right, where the sum equals to 0, in which case, well, the polynomial vanishes. And if you plug in the pair AB itself, well, you get some non-zero quantity. And these conditions imply that the polynomials are linearly independent. And the next step, one would like to, well, capture them in a finite dimensional subspace of polynomials in these variables. And it's not too difficult to squeeze out a subspace that has dimension 3 to the n by factoring this polynomial and reorganizing a little bit the terms there. Okay, so this leads to a very natural open problem, of course. And so improve on the sunflower problem. We have this bound from the slice rank argument, and we have a similar bound for the Trifference problem. It's almost the same problem if you look at them this way, except, well, we have 3 letters for one, and you have 2 letters for the sunflower problem. And you have this better bound that's an algebraic bound for the latter. So can one do something like that for the former as well? So of course the naive repetition of this argument does not really work, and yeah, it's kind of a tantalizing thing to try to think about. We couldn't really say do this, but who knows? Maybe someone can. There's a further plot twist that I want to tell you about. So turns out you can do even better. And this is a theorem that actually predates all this slice rank stuff. And of course, it's a theorem from the 80s of Corner and Martin. So they actually show that the Trifference set has size at most 2 times 3 divided by 2 to the n. And perhaps disappointingly, the proof is even simpler. And I don't know, even depressingly, it's not even algebraic. Or I don't know, maybe interestingly, it's not, depending on if you're the glass empty is epsilon full kind of person, like people in additive combinatorics are. So yeah, what the hell is going on? I can even tell you the full proof, not just the sketch in one slide. It's almost ridiculous. So I give you a Trifference set of maximum size, T3 of n, and we'll intersect it with this subset of the
Seems that we lost Cosmin, or?
Oh.
Yeah. Oh, it's better.
I'm back. I'm so sorry. My internet is a bit of a mess. Is it going on?
Yeah, it works now, but you should repeat probably with this intersect with.
Okay, I'll go from the top. So I was just saying that the proof fits here and like almost completely in this slide, not just the sketch. So let me just tell you, if I give you a Trifference set of maximum size T3 of n, just intersect it with this this box where you fix with the subset of the box where you fix the condition that, well, the vectors only have values 0 or 1 in the first coordinate. Well, this is a subset of A, so it's a Trifference set also, but you kind of forbid the Trifference property to happen in the first coordinate. So it's kind of a lower dimensional Trifference set. So this intersection has size at most T3 of n minus 1. And now, of course, it's not important if you do 0 or 1. You can do 1 or 2 or 0. Sum it up, you get this. 2 times T3 of n is at most 3 times T3 of n minus 1. And you repeat, and that's it. So yeah, it's kind of interesting. And this is quite general. As you can imagine, for a K hash code, this bound, you can do the same thing and you get this bound. And this is better than all the algebraic proofs that one can think of, at least the ones that we thought of. For instance, the linear independence trick argument gives A is at most K to this n divided by K minus 1, which is worse everywhere. So yeah, just a quick recap of what's happening. There are these bounds for the largest size of the question is, well, can we do anything better than this? And the answer is yes and no. And again, it was a really nice result of Fredman and Komlosh in '84. They showed in general that for every perfect K hash code, you have this bound, which, well, if one stares at these numbers carefully, you'll see that it improves on this inductive bound that I sketched for all K greater at least 4. And this generated quite a bit of activity. So in fact, there have been multiple papers just trying to refine this Fredman and Komlosh approach. It's a really nice probabilistic argument. And nowadays, I believe it has been improved everywhere for all K, at least 4. But now no results for K equals 3. The proofs, I mean, their theorem still goes through. It just gives, if you plug in here, K equals 3, this function that you get is just going to be worse than 1.5 to the n. However, one should say that, well, I'd like to say something about this, that, their main input in this theorem of Fredman and Komlosh is this really nice entropy lemma that actually, they state it in terms of entropy, but without entropy, it dates back to a paper of Hansel from '64. As you see in this talk, all the years kind of went reverse chronologically. So if I give you a complete graph on m vertices and you take a covering with bipartite graphs, an edge covering, then the log of the size of the complete graph you start with is at most the sum of these tau functions, where tau of gi is the fraction of non-isolated vertices in gi. That's kind of the main input, and there are different ways to apply this to get bounds, and this is essentially what people have been doing for perfect K hash codes to refine this Friedman-Komlosch approach. The reason I'm mentioning this is that, for instance, okay, you can replace, it's a rather robust lemma. You can replace the word bipartite with bounded chromatic number. You can do it for hypergraphs. You can take a 3-uniform hypergraph or a K-uniform hypergraph and do an edge covering there with tripartite 3-uniform hypergraphs. And the reason I wanted to bring this up is that, well, actually, it's not just that this result of theirs gives something worse for K equals 3, but actually this entropy lemma actually recovers the silly inductive bound too. And perhaps that's not really a surprise. If you're familiar with things like Loomis-Whitney inequality, it had even though this proof is kind of stupid, it has a feeling that is related with Loomis-Whitney, and somehow it's maybe not a complete shock that you can also recover it with some kind of entropy lemma like this. So this is what you do if you replace Km with the 3-uniform version, and when you try to apply this. So it seems like it's really some kind of obstruction to say something for K equals 3 with this method. So yeah, this is what we are intrigued about, and we wanted to say something to beat this 1.5 again. We couldn't, but we could do it for linear Trifference codes, for which, despite the additional very strong structure, it still wasn't clear how to beat this 1.5 to the n. So with Dimitri, we showed that, well, if I give you again a linear Trifference code, which meant a Trifference set in this box, which when regarded as part of F3 to the n, well, it's also a subspace, a linear subspace. Then the size of A is at most, well, this constant 1.3.16 to the n. So a bit better than 1.5 to the n. And so a bit more concretely, if you denote, well, if you take the dimension of this linear subspace, this dimension is upper bounded by this exponent there that we have, and divide by 4 minus some epsilon times n for some epsilon greater than 0. And yeah, so I won't say much about the proof. I know I'm short on time, but I should perhaps mention that well, our proof somehow uses ideas from everything that I kind of mentioned, although nothing specific as a black box. So due to the linear subspace structure, one can reformulate the problem somewhat conveniently so that algebraic methods can kick in, things like Alon-Furedi, Jameson, Brouwer, Shriver type things. So one can reformulate this problem into something about, I don't know, hyperplanes. And so one can use algebraic things, and then one can also incorporate probabilistic arguments in the style of this Friedman-Komlosch type stuff, and that allows you to beat this 1.5 to the n. Maybe a word also on the epsilon, although again it's kind of a technical thing to address in such a short description, but it was kind of it had some importance to us because it felt like it was kind of fighting over this probabilistic stuff of Friedman and Komlosch. So in some sense, it felt like a win that could maybe say something for the problem where you have just a Trifference set that's not a subspace, but you know, we really used linearity in a strong way. So okay, I'll end with another famous open problem combinatorics that's connected to all this, which I didn't state in its classical version. So I stated in terms of this this lemma of Hansel. So suppose I replace the word bipartite from before with triangle free. I give you a complete graph, and you cover it with triangle free graphs G1 up to GT. Can you show something similar? The log of the size of the complete graph is at most the sum of these tau functions. Again, I remind you, this was tau of GI was the fraction of non-isolated vertices. So this is a covering with edges where the GIs could be, you know, disconnected graphs. But I'll make it even simpler. You can upper bound the GI, the tau functions by 1 trivially. So that's a famous problem. It's completely equivalent, actually, with well, it's maybe not that obvious that it's completely equivalent, but just having the former result would trivially imply this upper bound for the Erdo-Schur conjecture about multicolor Ramsey numbers. So if you color the edges of the complete graph with M colors, so that no color class contains any monochromatic, contains no triangle, well, know that this function is upper bounded by something like t factorial, and it's a major open problem to prove that this is at most a constant that's independent of t raised to the power t. And so I said it's completely equivalent because it's actually, there's a way to go back to the original. So you can go from Erdo-Schur also to the top statement. So it's kind of interesting that if you replace bifield with triangle free, becomes a much more difficult thing. And yeah, even the case when, for instance, the graphs have bounded VC dimension. So the triangle free graphs, if you just assume that they have bounded VC dimension, it's not completely clear how to get this inequality. With some wishful thinking would be that, well, bounded VC dimension plus triangle free implies bounded chromatic number maybe, and then you can apply the Hansel lemma, but it's not true. There are graphs that have are triangle free, have small VC dimension, but really large chromatic number. And something along, but one can do something different for a weaker.
So yeah, we lost Cosmin again, or?
It's a bit laggy.
Yeah, Cosmin, so you said something like one can do something different, and then we lost you.
I'm not sure what I said. Oh, I said that I was mentioning this VC dimension variant.
Yeah, and then you started saying something new, and then we lost you.
Yeah, I just wanted to reference that it's not possible to follow this approach, but there was a recent paper of Fox, Pak, and Suk that proved the conditional result for the Erdo-Schur conjecture on the somewhat weaker VC dimension assumption with different kind of ideas. Not very algebraic, but still a very nice paper. So that's all I wanted to say. Thank you all for listening.
Thank you.
Yeah, let's thank the speaker first. Yeah, we get a couple of minutes for Q&A, right? Andrew?
Yeah, sure. I mean, yeah. Next talk is at 40, so we have to.
Yeah, a couple of minutes for.
Okay, I have a question. So, but can you get something just for linear cap perfect hash codes? If you use just maybe the same technique, or?
Yeah, that's a great question. So you need prime k. So when k is in FP2, so you can define p perfect p hash codes, I guess, for a prime p. And you can ask the same question. It's very likely, although I don't think it's completely obvious or straightforward, but it's likely that the methods can give something. It's also perhaps interesting for submodules of z mod k to the n. So if you take a perfect k hash code, that's a submodule. Maybe also you can improve. But there, I think one needs some different ideas because we really use the field structure a bit.
But as for the construction side, so what do we know about some like
for k perfect k hash codes?
No, just for say 3 different sets.
Yeah, so there's this corner Martin lower bound.
You said that there is something like a product type construction.
Yeah, so yes and no. This corner Martin lower bound, which is this. Well, maybe I should go to
I see.
To the beginning. So it is a deletion argument. I mean, it's not really the naive deletion argument that one can do to get this an exponential lower bound. It really uses this linear code as an input also in the construction. So it's kind of a mix between product and probabilistic argument. It's kind of a clever construction.
I see. I just know that there was some improvement just for K-perfect hash codes recently, also using a combination of probabilistic arguments and some explicit construction.
Yeah. So that's also a great question. I think there the situation is not that nice actually. So surely there's some deletion lower bound that one can do, but I think this code for the Trifference problem is somewhat special. This Conway-Sloan code. So I don't think you can get things as that of that quality. It might be just that naive deletion is the best thing that you can do there. So I think the numbers, or I don't know. I didn't really try that much to work on lower bound. So maybe I'm a bit wrong. But it just this Trifference argument felt a bit special to me for the case k equals 3.
Okay, thank you. Yeah, I know that the converse bounds are much more interesting for at least theoretical computer scientists also.
Now I have a question. So it's interesting to see that when you replace the set 0, 1, 2 to 1 psi square, you get some improvement. Is there in some way that this new set 1 psi square is somehow optimal? Or have you maybe tried some other roots of cubic equation?
Yeah, I'm not sure. So I thought about this, but yeah, I don't know anything really non-trivial to tell you more than this. It just seems, yeah, kind of somewhat puzzling that you can beat the slice rank argument with this trick. I'm not sure. Yeah, there's definitely some kind of clear limitation for these algebraic methods. Like same for the slice rank argument. This bound is really, you cannot really improve upon it by taking a different tensor. There were some papers and blog posts about this. It's possible that something of this sort is true for this linear independence argument also, that maybe it's a natural limitation unless you use more of the combinatorics of the problem. But it's unclear exactly how would that a statement like that would go. I don't know.
Are there any other questions? Okay, I guess let's thank Cosmin again. Thank you.
Yeah, it was very interesting. Thanks, Cosmin.
Thank you, everyone.